today's lesson. Today we're going to look at stretches. And stretches can go in two main directions, at least the ones that we're going to look at. The first group of stretches that we're going to look at are kind of the easier ones, and that would be a vertical stretch. Now, we say stretch, but in a sense, to kind of get a grasp of this, it could either be a stretch which makes the vertical distance bigger, or it can actually be a compression, which means the vertical distance is getting smaller. Let me just show you what I'm talking about here with a very simple comparison. Suppose we had a graph that looked something like this. Say one part of the graph perhaps went up 2 units, with a little circular part that went like that. Okay, just a very simple little demonstration. If we wanted to compress this graph vertically, then this point here, which has coordinates 1, 2, the y value would become compressed. Say we're going to compress it by a factor of 1/2. So it would only go up 1 unit at that point. Now, these 2 points here have a y value of 0, and so they're not going to change. So, for example, this point, that's going to be an invariant point. It's not going to change at all. So if we wanted to compress by 1/2, the resulting graph would look something like this. Okay, every vertical distance is going to be now half as big as it used to be. And so that would be an example of compressing by 1/2. Now, by the same token, if we took a different graph, well, actually, let's take the same graph where we just go, whoops, there we go. We're going to go up 2 again. And so we're going to basically look at the same original graph. If we wanted to, say, stretch that or expand it vertically, let's say by a factor of 2, well, what are we going to see as a result? For example, this point here, which had a vertical distance of 2, will now be expanded by a factor of 2, so it'll go up to 4. So it's going to be should have drawn a little bigger, but that doesn't matter. It'll be up to there. So the resulting graph would look something like this. So that's when we say it's going to vertically be expanded by a factor of 2. Now let's look specifically at an example and how we actually affect the function to produce that kind of a expansion or compression. The rule is pretty simple, and it's pretty logical if you think about it. If we have a function, y equals f of x, if we want to take these y values and let's say we want to double them, then what we want to do is simply take f of x here and put a 2 in front. And that'll have the effect of taking the y value and timesing it by 2. So in short, here's what the rule is. We have y equals, we'll just call it k times the function. And what that does is, vertically, you're going to affect change by a factor of k. So in other words, if we took an example like the square root of x, and we decided we wanted to vertically triple it. Okay, so we want to do the following thing. Y equals 3 times root x. So what's that going to do to our graph? Well, and I'm going to draw both the original and the transformed graph on the same grid here. In the original, we had 0, 0, 1, 1, and then as another good point, we'll go 1, 2, 3, 4, which goes up 2. So those are some points in the original. I'll just do that with a dotted graph here. So there's f of x. And now the idea is we're going to transform that and vertically expand each distance by a factor of 3. So instead of going up 1 unit, we're going to go up 2, 3. It's 3 times as much. Instead of going up 2 units over here, we're going to go up 3 times 2, or 1, 2, 3, 4, 5, 6 units. So this would be our transformed graph. Plowing right through my algebra there. So that's what our transformed graph 3 f of x would look like. All vertical distances have been tripled. Okay, so that's an example of how we can do vertical stretches, or if you like, compressions or expansions, a little bit more exact terms. But what about horizontal? Let's look at some horizontal changes. And what I'm going to do, I'm just going to start off by giving you the rule, showing you an example. This one's a little bit more slippery, but I think with an example we can sort of get a grasp on how that works. The rule is, if you want to do a horizontal change, well, what you have to do is this. You have to put the number that's going to affect the horizontal change right in front of x. Now, the tricky part of this isn't so much that you're going to put that number in with x, but the change that will occur is going to be that number's reciprocal. So the factor of change is 1 over k. Now, probably the best way to see this is if I work through an example. So let's take our old buddy, y equals the square root of x. And what we're going to do is we're going to put maybe a 2 in front of the x and see how that would affect our graph. Well, again, I'm going to do the original graph, okay, and show its points. We have 0, 0. 1 to the right corresponding to up 1, and 2, 3, 4 to the right corresponds to up 2. So again, I'll do a dotted graph. So there's f of x. Now what's going to happen is the following. If I take some number, and the numbers are going to be a little bit funny because you're kind of thinking backwards here, but in order to achieve a y value of 1, if I look at this particular graph here, the x that I need to plug in is going to be 1/2, because 2 times 1/2 makes 1, and the square root of 1 is 1. So to achieve the same y value of 1, I only want to put in an x value of 1/2. So that point is going to be there. So what I'm actually going to be doing is horizontally, what used to be 1 to the right, up 1, is now only 1/2 to the right and up 1. It's being compressed horizontally by a factor of the reciprocal of that number, by a factor of 1/2. So let's put on a couple more points and finish our graph. Another good point that we used to have was 4 and up 2. So what we're now going to do to accomplish the same y value, instead of 4, we're going to put an x value of 2 in. Because an x value of 2 times 2 makes 4. Square root of 4 is 2. So if we go 2 to the right in our new function, we're going to have the same y value of 2, which is about here. So here's what our compressed graph would look like. This is f of 2x. So horizontally, it's compressed by a factor of 1/2. So I just said compressed. And by the same token, let's have a look at just a couple of algebraic analyses of some functions and how they would look. So what I'm going to do is just take a different function this time, I think, And let's say that function looked something like this. Say f of x was the absolute value of x, and we'll put in a minus 3. And let's say this time what I want to do is I would like to have it compressed horizontally by 1/3. So I want to take what normal graph is and kind of compress it by a factor of 1/3. Well, what we've seen is, if I take my original function, what would I want to put in front of x that accomplishes this 1/3? I want to put in a 3. Again, remember, it's the reciprocal of this number that becomes your factor of compression or expansion. In this case, it's compression. Just to sort of finish it up and show you what the graph might look like, what do we have happening here if we want to take our function and put a 3 in front of the x? Well, the function we'd want to graph would look like this. Absolute value of 3x minus 3. And just to convince you that what we have here is indeed going to be horizontally compressed by 1/3, I'm just going to look at a couple of foothold points to show you that. So I'll just put a little table over here. If we plug in a 0, well, 3 times 0 is 0, minus 3, so negative 3. So there we have the 1, 2, 3, kind of the vertex of the graph, which is what we expected, a downward pull or a translation of minus 3. At this new location, we're now going to be looking at this horizontally compressed graph. Okay, well, what do we have happening there? If we go 1 to the right, what are we going to get? 3 times 1 is 3. The absolute value of 3 is 3. Take away 3 is 0. So, if we plug in an x value of 1, in the old days when we just had the absolute value of x, we would have gone up 1. This time we're going up 1, 2, 3. So, it has in fact a kind of an overlap effect. It almost looks like some vertical change, and that is another way to interpret this. However, we're going to interpret this horizontally. So we have this 1 to the right and up 3. Now, in order to accomplish a upward of 1, like the old function used to, how far would we have to go to the right? And this is a little bit slipperier, but I think it makes a very valid point. If we just put in 1/3 for our x value, 3 times 1/3 is 1. The absolute value of 1 is 1. Minus 3 is negative 2. So what do we have happening there? Well, if we go 1/3 to the right, which is a little bit hard to graph here, we would want to go up to negative 2, which would be about there. What we're getting is, there's our graph. Kind of running out of ink here, but there's our graph. And, of course, the sort of mirror image of it due to symmetry on the left side. But what we're illustrating here is the following. You can look at this as a vertical change. We're interpreting it right now as a horizontal change. And to accomplish this same y value of going up 1, we only went 1/3 to the right. So the whole thing has been compressed horizontally by a factor of 1/3. Another way to illustrate this whole compression and changes horizontally or vertically without actually looking at a particular function is to kind of analyze a graph, which is kind of what we did earlier. And the only difference that I'm going to do from what I did before is talk about something that we call the zeros. Now, you're probably familiar with that from your other work, but if you have a graph that looks like this, okay, and this graph, I think what we'll do is go maybe 3 to the right, very simple graph, kind of like the one I did before, and do something like this here. So that's our little f of x. From our original, we could say, well, the zeros of this graph are 0 and 3. So here's where the questions are now going to be somewhat changed. Suppose what I did was something like this. That's f of x. Suppose I made some little modifications like negative 1/3 x and asked you for the zeros again. Now I threw in a little extra twist there, but let's have a look. What would the zeros now be doing? Well, let's first of all analyze what the graph is going to become. Now, as we saw earlier with reflections, when you put a negative in front of the x term, now the fact is I put in a negative 1/3, but the negative itself has the effect of reflecting across the y-axis. We have to keep that in mind. We're going to reflect across the y-axis. So I'm just going to make a little note here. We have some y reflection going on. And the other thing that we're doing is horizontally, the reciprocal of this is times by 3. So not only are we reflecting across the y-axis, but all horizontal distances are going to be tripled. So where are those zeros? Well, they're at 0 and they're at 3. So if we reflect our graph across, well, 0 is going to stay put. That's still going to be what we call an invariant point. It's not going to move. But this 3 is going to be 3 times as far reflected across. So it would have gone over to 9 and gets reflected across. I don't think I'm going to have room here, but the idea is 1, 2, 3, 4, 5, 6, 7, 8, 9. So now we can identify where those zeros are going to be. Graph would look something like that, way over to there. So we're going to still have 0 as one of our zeros, and negative 9. So that we get not by drawing a very good graph here, but by a very simple analysis of what these little numbers, what effect they have as far as transformations. So I think that's where we're going to stop for today. So we'll catch you later.